All right, in this problem, we are going to examine the continuity, or rather the discontinuity of a function at a certain value. We have to decide what type of discontinuity it is, and we have to examine whether the function has any discontinuities at other points. This is a bit of a strange function, this absolute value of x divided by x. What you might be able to do is look at the piecewise definition of the absolute value function, because absolute value of x is actually a piecewise function itself. For positive values of x, it's simply x, and for negative values of x, it's negative x, which makes it positive. You can choose either one of these to adopt the or equal to, and it will leave the function unaffected. It doesn't really matter. A lot of people like positive numbers, and so they would do it that way. But the first question here is, show that this function is discontinuous at the value x equals 0. Remember that continuous means something very specific. Continuous means this, that, or continuous, I'll say continuous at x0. That means that f of x0 equals the limit as x approaches x0 of f of x. And these conditions mean that f of x is headed somewhere, and it arrives. Notice that a simple requirement here is that f of that value, f of x0, or in this case, f of 0 itself, has to be defined in the first place. If f of x0 is not defined, the function cannot be continuous. Because think about what it means if f of x is not defined at that value in the first place. If f of x, or in this case f of 0, is not defined, then the quantity on the left-hand side of this equation doesn't even exist. So if it doesn't exist, there's no chance for it to be equal to the value of the limit, regardless of whether the limit exists or not. So the function is discontinuous because f of 0 is not defined. This is an easy one. But now we get to a little bit of a tougher question. What type of discontinuity is this? You should familiarize yourself with the types of discontinuities. There's removable, sometimes known as a hole. That's when a function is moving along and then all of a sudden has a single hole punched out of it. And sometimes it can adopt an alternate value either above or below, but it doesn't have to. So this is a removable discontinuity. So is this. So is this. And it doesn't depend on whether the function has a value at that point or not. The point is that limit as x approaches the value exists, but the limit is not equal to the actual value of the function. And it can fail to be equal to the value of the function for various reasons. Maybe, as in this picture right now, the function doesn't even exist at that point. If the function doesn't exist at that point, then the limit cannot be equal to it because there's nothing to be equal to. But if I also assign the function some value above or below, then the limit value, which is right here, that's where the limit is, then the limit is still not equal to the actual value of the function, which is in this case above it. There is also jump. This one is like this, where you have a function with the left and right hand limits each equal and finite. I'm sorry, each finite but not equal. So this would be that the limit of x going to x naught from the left of f of x is not equal to the limit as x approaches x naught from the right of f of x, and both limits, both of those one-sided limits exist and are finite. Now, the reason that I want that condition is that there's a third type of discontinuity, and it's an infinite discontinuity, sometimes called, often called a vertical asymptote. And this is, everyone knows what this looks like. It's something like this. It can go up on one side, down on the other. It can go up on both sides. It doesn't really matter. The important thing is that the limit as x approaches x naught, either from the right or from the left, is positive or negative infinity. I didn't write the function in this case, but this is the type of behavior that means that there's a vertical asymptote. It goes up on both sides. It goes up on one side, down on the other. It goes down on both sides. If both of the limits on either side of a point are either positive infinity or negative infinity or some mix of those, then that's called a vertical asymptote. So in this case, we have to decide what sort of behavior does this function exhibit at x equals 0. I want you to think about the values that this function actually takes on. For x greater than or equal to 0, absolute value of x divided by x equals, think about this, this is numbers like 5 or 13 or 107. The absolute value of all of those numbers is the numbers themselves. And so when you divide the number by the number itself, it's 1, right? Technically, I should be saying it's not really greater than or equal to. We'll deal with the equal to in a second. What about for x less than 0? Well, now the top of this is forced to be a positive number, but the bottom is the very same negative number. That means that all of these are going to be -1. So I want you to think about the effect on the graph of this. For all values greater than 0, this is simply +1. For all values less than 0, it's -1. What about at 0? Does it have a value? No. We saw that in the first part of this question. The reason that it's discontinuous is most simply attributed to the fact that the function has no value in the first place. If it has no value in the first place, it doesn't have a chance of being continuous. But now you can see this lines up very well with this sort of behavior. So it is a jump discontinuity. It's because the limit as x approaches 0 from the left-hand side of absolute value of x over x is, now we're talking about approaching from this side. See, from the left, it's going toward the value of -1. Well, let's write that down. That equals -1. But the limit as x approaches 0 from the right-hand side of the absolute value of x divided by x, now we're talking about approaching it from this side. And this, you can tell, approaches +1. This means that the left and right-hand limits are not equal. And that is exactly the condition that we had for a jump discontinuity. So this function is discontinuous at the value x equals 0. It is a jump discontinuity. Now, the other question is, does the function have any other discontinuities? Believe it or not, the answer to this is programmed into what we have already done. Because I want you to look at this branch of the function. This is going to be 1 forever and ever and ever. Because for x greater than 0, this function is always going to have the value of 1. For x less than 0, it will always be equal to -1. And so this branch is never going to do anything funny after this part of the picture. This branch is also never going to do anything funny after this part of the picture. So what this means is no other discontinuities ever. And that's that.